Okay, we're going to get into conservation of energy, and you do have these guided notes in your packet. So in some mechanical systems, energy is completely conserved. So what that means is that it's not being lost or gained in that mechanical system. Instead, it's just transferred from one form to another. It doesn't really happen in real life too often because you're usually going to have energy lost to some type of thing like friction. But for now, we're just going to look at those ideal situations where all of the mechanical energy is conserved. The three forms of mechanical energy so far that we've seen, just to refresh your memories: elastic potential energy, which is energy stored in a stretched or compressed spring; kinetic energy, which is the energy stored in an object's motion; and gravitational potential energy, which is energy stored in an object's height above the base level. So what we're going to be looking at is conservation between those three types of energy. So solving conservation of energy problems. First, you need to start with a diagram if you don't already have one, and the diagram has to show what's going on. So you want to label it with A and B to show initial and final states. If you've got more than two things happening, then you go to C or D. So A, B, C, D, whatever's happening, you need to show each part of the problem. You also need to label your base level to show where your height is equal to 0 meters. For some problems, that is arbitrary, and that's fine. You just need to make sure that you're showing where that base level is. Next, you want to list your given and find, and make sure that you add subscripts. And what I mean by subscripts are A or B or C or D, because you want to show like what the speed was at A, what the stretch was at C. So that's very important that you're using your subscripts, and you'll see that when I do the examples. Third thing you need to do is make your energy bar charts to show what form of energy is in each state. These are required for any conservation of energy problem. And as we saw from the bar chart worksheet, the number of boxes should be equal between the two bar charts. So however much energy you had in A, that's how much energy you need in B or C or D. Number 4 is list the following 3 steps. And again, I'm just going to do this for 2, like a part A and a part B, but you could have equals farther than this. So the first step, energy at A equals energy at B. Or if you have like a C or D, equals energy at C equals energy at D. That's an E, not a D. So this is the first step. The second step is the kind of energy at A equaling the kind of energy at B. So what I mean, like, is it kinetic energy at A? Is it gravitational energy? You want to show what kind. This should be E kind A equals E kind at B. And then the third step is to write the equation for each one. So the equation for your types of energy at A equaling the equation or equations for your energy at B. Okay, and the last 3 steps, isolate what you're solving for, put in the numbers and solve, and make sure your units make sense. So those are the same 3 that we would look at with problem-solving guidelines, and of course you need to round. But the main thing for this is making sure that you have those 3 steps in number 4. Energy at A equals energy at B, kind of energy at A equals kind of energy at B, and the equation at A equals the equation at B. Those are things I will look for whenever I'm grading tests or quizzes. Okay, so the first example, and again, this is in your packet on the back of the page with the notes, tells us that a 5-kilogram cart is compressing a spring with a spring constant of 75 newtons per meter at a distance of 0.5 meters. Once the spring releases that should say cart, it begins to move. How fast is the cart moving? So our diagram. You've got a spring compressing a cart. The cart is at rest. And then the spring releases the cart, and the cart begins to move. I'm going to label this A and label this B. So looking at the steps, you're drawing your diagram, making sure to label A and B to show initial and final states. Given information, we know that the mass is 5 kilograms. Spring constant is 75 newtons per meter. Compressing the spring at A, so my delta XA is 0.5 meters. Why didn't I use a subscript for a mass or K? Because those things can't change. Delta X can. I know that my speed at A, since it's at rest, is 0 meters per second. And what am I looking for at B? I'm looking for the speed. So steps 1 and 2 of the problem: draw the diagram, making sure you're labeling your initial and final states, list your given and find, making sure that you're labeling with your subscripts. Next thing we want to do is draw our energy bar charts. So we really just want to draw these out. And yes, they can be a pain, but I do them too. So our bar chart for A, our bar chart for B. And at the top we want to label EEL, EK, EG, EEL, EK, and EG. So at A, what kind of energy do I have? If this is the base level, it's not moving, it is compressing a spring, and it's at the base level. All of my energy at A is elastic potential energy. At B, the spring is no longer compressed, it's still at the base level, but now it's moving. So the amount of energy at A equals the amount of energy at B. It's getting transferred from elastic potential energy to kinetic. Now, 3 steps that I want to list, and these come right from the bar charts. First step, energy at A equals energy at B. Second step, the kind of energy at A. So this is EEL at A equals EK at B. Third step, my equation for EEL. 1/2 M, 1/2 K delta X at A squared equals 1/2 M V at B squared. And now I can solve. My 1/2s cancel out since it appears on both sides, so K delta X at A squared equals M V at B squared. Isolating for V at B, I get K delta X at A squared over M equaling V at B squared. My K, 75 newtons per meter, times delta X at A, 0.5 meters squared, divided by my mass of 5 kilograms equals V at B squared. So we get 3.75 meters squared per second squared equaling VB squared. Taking the square root of that, 1.93 keeps on going, meters per second equals VB. This is only 2 sig figs, so my speed at B is about equal to 1.9 meters per second. Before I go on, let's take a look at these units. Okay. On the top, we have a Newton per meter times meters squared. So this becomes a Newton times a meter. And on the bottom, we have kilograms. Inside a Newton is a kilogram meter per second squared times meters over kilograms. That cancels out those kilograms, leaving us with meters squared per second squared, which are the units for V squared. Square root of those is how we got our meters per second. So when I say look at the units, if you made a mistake anywhere, these units are going to really kind of clue you into that. Just break everything apart and kind of see how those work out. I'll do one more example like this where there's only one type of energy, so I'll do the next one, and then I'm going to do, you know what, never mind, I'm not going to do the next one, I'm going to do the fourth one. So I'll give you the answers, I'll have these in class if you're interested in the second and third examples, but I will do the fourth one so you can see what happens if you've got more than one type of energy. Okay, so this is the fourth problem in your packet, and it's written like this. There is a typo that I will correct here. It tells us that a ball rolls on a flat surface above the ground with a speed of 5 meters per second. It then falls to the ground and continues to roll at a speed of 4 meters per second. How high was the surface? The typo is this. We need to make this 5 a 4 and this 4 a 5. And that was my mistake. So it's starting out at 4 meters per second on the surface, and then it's going to be 5 meters per second once it hits the ground. So when we draw our diagram, you've got the ball rolling across the surface, and then it's going to fall to the ground and roll faster. I'm going to label this A and that B. This is my give and find. we know that the speed at A is 4 meters per second. We know that the speed at B is 5 meters per second. And we know that the height at B is 0 meters. And we know that if we label this right here as our base level. Makes sense, ground is usually the easiest thing to make the base level. And what's it asking us to find? We want to know the height at A. So let's draw our energy bar charts. We only need two since we've got an A and a B. And you will get used to drawing these. I've drawn about 1.5 million. So we have EEL, EK, EG, EEL, EK, EG. Here's my bar chart for A. Here's my bar chart for B. At A, the ball is rolling across the table, so it's got speed or motion and it's got height. There is no spring involved. So we've got kinetic and gravitational. At B, there's still no spring. It is moving, but it's now at the base level. I had 4 boxes in A, 2 and 2, so I need 4 boxes in B. I'm going to go up to 4. Okay, first step, we're going to say the energy at A equals the energy at B. Second step, the kind of energy at A. So if you look at the bar chart, you're going to have kinetic energy and gravitational potential energy. So all that means is adding those two together is going to get you your energy at B. So I have 2 kinds of energy at A. This will be EKA plus EGA equaling the kind of energy at B, EKB. And now the equations. And this is why subscripts are really important. We have 1/2 m v at A squared plus mg height at A equals 1/2 m v at B squared. Since we have 2 speeds, it's really critical that you have these 2 subscripts to show the difference because they are not the same. You'll notice that in this case mass appears in all 3 of the terms, so we can cancel mass out. This is not always true, but now we can for this one. And then I don't like fractions, so I'm going to get rid of the 1/2 and multiply everything by 2. So just multiplying both sides by 2 to get rid of this 1/2. You don't have to do this step, it's just something I like to do. So this leaves us with VA squared plus 2G height at A equals VB squared. We're looking for height at A, so I'm going to isolate that. 2G height at A equals VB squared minus VA squared. Oops. Dividing both sides by 2G, we get height at A equals VB squared minus VA squared over 2G. Okay, now let's just put in the numbers. So height at A equals 5 meters per second squared minus 4 meters per second squared over 2 times 9.8 meters per second squared. Quick look at these units. You get meters squared per second squared on the top, so that gets rid of the second squared. On the bottom you've got the meters, so we're going to be left with just meters on the top. Height should be measured in meters, so that's a good sign. So we get 25 minus 16 over 19.6. This gives us for our height at A 0.459, keeps on going, meters, only 1 sig fig, so height at A is approximately equal to 0.5 meters. So this is how we solve problems dealing with conservation of energy. It's crucial that you use the bar chart because from the bar chart is where you get your 3 steps, the EA equals EB. And really from there it's just a matter of recognizing what type of energy is at A, what type of energy is at B, and then algebra.